The universe moves like a living breath, an endless exhalation unfolding into the abyss of nothingness. Across this invisible tide, galaxies drift apart, not with noise or fury, but with a silence more profound than any void. Each one sails outward, like a solitary ship leaving a forgotten harbor, carrying within its light the memory of a single, fiery dawn, the birth of all things in the crucible of the Big Bang. For over 13 billion years, this expansion has been the rhythm of existence, the silent law written into every star, every planet, every atom. Yet hidden within this grand unfolding is a question as haunting as it is unavoidable. What if this cosmic flight is not eternal? What if the great breath of the universe falters? Science now knows that expansion began in a storm of fire, yet the force that drives it remains cloaked in mystery. Some call it dark energy, a name that is more shadow than explanation, and with every passing observation, the enigma deepens. What happens if this expansion slows, halts, or reverses? Does space itself collapse into silence? Does time unravel with it? Or does something stranger take its place, a transformation, beyond the grasp of thought? The story of the universe is not merely about its beginning, but about its fate. And hidden within that fate is a question that cuts to the very heart of existence. When expansion ends, what becomes of space itself? On a clear night in the early decades of the 20th century, beneath the cold air of the San Gabriel Mountains in California, the dome of the Mount Wilson Observatory turned its great eye to the stars. Inside, Edwin Hubble worked in patient silence, surrounded by glass plates that captured the faintest whispers of light from galaxies unimaginably far away. At the time, they were still called nebulae, mysterious clouds whose true nature was uncertain. To the unaided eye, they appeared as smudges, barely distinguishable from the darkness. But through the telescope's mirror, they revealed spiraling forms, vast islands of stars suspended in the deep ocean of the cosmos. Hubble's task was deceptively simple: to measure the distances to these nebulae and chart their place in the universe. Yet the more carefully he studied their starlight, the more it betrayed an unexpected story. The colors were not quite as they should have been. They were shifted toward the red, stretched like echoes pulled thin by distance. This phenomenon, first recorded by Vesto Slipher, hinted at a strange velocity. The galaxies appeared to be moving away. Hubble refined these measurements, comparing the degree of redshift to the distances he could calculate through the brightness of Cepheid variable stars. Slowly, a pattern emerged. The farther a galaxy was from Earth, the faster it seemed to recede. This was not mere motion through space. It was something far stranger. The galaxies were not fleeing through a static void. Instead, the very fabric of space itself was expanding, carrying the galaxies apart like leaves drifting on the surface of a swelling river. The universe, long thought to be eternal and unchanging, revealed itself to be alive with growth. So, shock of this revelation rippled through the scientific world. For centuries, the cosmos had been imagined as a grand celestial machine, steady and timeless. Philosophers, from Aristotle to Newton, envisioned a universe that stretched infinitely, constant in its form. Even when Einstein completed his general theory of relativity in 1915, his elegant equations pointed to something disturbing: a universe that could not remain static. Gravity, acting on such vast scales, would inevitably cause collapse. Yet Einstein resisted this conclusion. It conflicted with the prevailing intuition of eternity. To counterbalance gravity, he introduced a new term into his equations: the cosmological constant, a repulsive force designed solely to maintain a stable, eternal universe. When Hubble's results reached him, Einstein confronted the contradiction. The galaxies were receding, space was stretching. The static cosmos he had sought to preserve was an illusion. In later years, he would look back on that decision and call the introduction of the cosmological constant his greatest blunder. Ironically, the concept he abandoned would return decades later, resurrected in a different form, as the mysterious force now known as dark energy. The discovery of expansion marked a profound turning point. The ancient vision of a universe without beginning or end crumbled. In its place emerged a dynamic cosmos, a universe with a history, a universe that evolves. If it was expanding now, logic demanded it must once have been smaller. If traced backward, the galaxies would converge, compressing into a denser, hotter, more compact state. What Hubble had revealed carried within it the seed of the Big Bang, the notion that the universe had a beginning in time. This was more than an astronomical finding. It was a philosophical upheaval. For the first time, science suggested that the cosmos itself was not infinite in age, but finite, with an origin in a moment of unimaginable violence and creation. Humanity, long comforted by the idea of an eternal stage, now stood upon shifting ground. The stars were not lanterns pinned to a fixed dome, but travelers swept along by an invisible tide. Hubble's measurements, recorded in careful graphs and published with cautious words, were the first whispers of a truth almost too vast to comprehend. The universe was not still. It was unfolding, its dimensions stretching, its distances growing. Space was not a void into which galaxies moved. Space was the very medium expanding, carrying the galaxies apart. This realization was subtle, but it redefined everything. The early 20th century became the cradle of a new cosmology. With Hubble's work, the notion of a living, evolving universe took root. Einstein's equations, stripped of the constraint he had imposed, described a cosmos in motion, and in observatories across the world, astronomers began to glimpse the outlines of a universe far stranger than they had ever imagined. This was the birth of a new vision, a universe that breathes, that grows, that possesses a history, and therefore a fate. A vision in which the night sky is not a map of permanence, but a fleeting moment in an unfolding story. And hidden within this revelation lay a haunting implication. If the universe is expanding now, what awaits when the expansion ceases? Does the cosmos settle into stillness, collapse into ruin, or tear itself apart in a final act of dissolution? Hubble could not have known the questions that would echo from his discovery. Yet on those nights atop Mount Wilson, as the cold desert, air carried starlight into his telescope, he opened the door to them. And through that door, humanity stepped into a universe alive with mystery, forever changed by the realization that space itself is not eternal in form, but a fabric that stretches and evolves, carrying us toward an uncertain horizon. The revelation that the universe was expanding arrived not as a quiet refinement of existing knowledge, but as a thunderclap against centuries of belief. For the human mind, nurtured on the dream of an eternal cosmos, the idea was nothing short of heretical. Philosophers and astronomers alike had long found comfort in the thought that the universe stretched infinitely in both space and time, without beginning and without end. It was a vision of stability, of permanence, of a cosmic stage that required no origin story. Yet Hubble's discovery, etched into glass photographic plates and measured in the redshifts of distant galaxies, threatened to dismantle this ancient assurance. The logic was undeniable. If galaxies are receding today, then yesterday they were closer, and long before that, closer still. The clock of cosmic history, when rewound, pointed not toward endless stability, but toward a singular origin. A moment when all matter, energy, and space itself were compressed into a state of unimaginable density and heat. This concept, though now familiar, was revolutionary in the 1930s. It implied a birth, a beginning of time itself. In that instant, the eternal universe dissolved, replaced by a cosmos alive with history, motion, and inevitable destiny. The scientific world reeled at the implication. Some embraced it, while others recoiled. Among the most vocal skeptics was the British astronomer Fred Hoyle. To him, The notion of a universe emerging from a fiery singularity seemed absurd, even unscientific. He and others advanced what became, known as the steady-state theory, a model in which the universe could expand while remaining eternal. In this vision, as galaxies drifted apart, new matter would continuously form, filling the gaps, maintaining the same density forever. There would be no beginning, no end, only a cosmos eternally replenished. Hoyle dismissed the rival theory with a phrase intended as mockery. During a BBC broadcast in 1949, he referred to the idea of a primordial explosion as the Big Bang. The name, meant as derision, would instead become its permanent mark. For decades, the two visions, the steady-state model and the Big Bang, competed fiercely for dominance. Observatories scanned the heavens for evidence for some lingering clue hidden in starlight that might reveal which story the universe truly told. The tension was more than scientific. It carried a profound emotional weight. An eternal cosmos allowed humanity to believe in permanence. The stars, though burning, seemed woven into a fabric that would never unravel. A universe with a beginning, however, was a universe that could also have an end. If there was a birth, there might also be a death. To accept expansion was to confront mortality on a cosmic scale. The galaxies, their light serene in the night sky, became reminders of an unstoppable process, a story that had begun and one day would conclude. Einstein himself had struggled with these consequences. His equations of general relativity naturally permitted a dynamic universe, but he resisted their implications until Hubble's observations left no room for denial. The most elegant mathematics in physics pointed toward a finite past, and perhaps a finite future. What he once sought to suppress became unavoidable. The universe was not a tranquil backdrop, but an evolving entity. In the decades that followed, the scientific shock only deepened. Observations accumulated. Radio telescopes began to probe the universe beyond visible light. Astronomers mapped the faint glow that seemed to bathe the entire sky, the cosmic microwave background, relic radiation from the very beginning. Its discovery in 1965 by Arno Penzias and Robert Wilson delivered the fatal blow to the steady-state model. Here was fossil light, stretched across billions of years, undeniable evidence that the universe had once been hot, dense, and young. The Big Bang was no longer speculation. It was reality etched into the cosmos itself. The implications pressed upon human thought like a weight too vast to bear. For the first time, humanity stood face to face with the finite. The universe had not always existed. It emerged, it grew, it aged, and if it could begin, then it must also face an ending. Astronomers began to speculate on possible fates: eternal expansion, eventual collapse, or something stranger still. But the central truth remained inescapable. The cosmos was no longer a stage for timelessness. It was a story, and every story carries within it the seed of conclusion. This realization was both terrifying and sublime. Terrifying, because it stripped away the comfort of eternity. Sublime, because it placed humanity within a narrative of grandeur, a chapter in a book written across billions of years. To look at the stars was no longer to see eternal fixtures, but distant travelers sharing in the same unfolding journey. Their receding light carried both a reminder and a warning that everything, from the galaxies to the atoms in human bodies, is part of a universe that began and will one day transform again. Thus, the scientific shock of expansion was not confined to equations or telescopes. It was a shock to the very imagination. It forced humanity to reconsider its place, to confront not only the fragility of worlds, but the impermanence of the cosmos itself. In Hubble's redshifts and Einstein's equations, in Hoyle's resistance and Penzias's serendipitous discovery, the universe revealed its greatest secret, that it is not eternal, not fixed, but alive. And with that life comes the inevitability of change, of birth, and of eventual death. The discovery that the universe was expanding was a revelation, but it was only the beginning. To glimpse a pattern is not to understand it. The galaxies receding in Hubble's measurements whispered of a vast story written into the fabric of space-time, yet the details of that story were still hidden, scattered like fragments of an ancient manuscript. To reconstruct the universe's past and foresee its fate, astronomers needed more than a few lines of evidence. They needed to map the expansion itself, to trace it across cosmic history, and measure its rhythm with precision. The first great clue arrived not from a telescope pointed at galaxies, but from an unexpected glow that seemed to come from every direction in the sky. In 1965, Arno Penzias and Robert Wilson, working with a radio antenna in New Jersey, stumbled upon a faint background signal. No matter where they aimed, the noise persisted, steady and cold. It was the afterglow of creation itself, the cosmic microwave background, radiation released when the universe was only 380,000 years old, long before stars and galaxies had formed. This ancient light, stretched by billions of years of expansion, offered a direct imprint of the young cosmos. With its discovery, the universe revealed a second voice, deeper and older than the galaxies. If galaxies traced expansion across billions of years, the cosmic microwave background carried the signature of its first breaths. To measure it was to place a marker at the beginning of cosmic time. In the decades that followed, satellites were launched to study this relic radiation in exquisite detail. COBE, the Cosmic Background Explorer, launched in 1989, delivered the first full-sky maps of this ancient light. It confirmed that the background was astonishingly uniform, but not perfectly so. Tiny fluctuations in temperature, 1 part in 100,000, appeared as mottled patterns across the sky. These subtle variations were the seeds from which galaxies and clusters would eventually grow, shaped by gravity as the universe expanded. Then came UMAP, the Wilkinson Microwave Anisotropy Probe, launched in 2001. Over 9 years, it refined the cosmic map, measuring the geometry, composition, and age of the universe with precision never before imagined. The data revealed a cosmos 13.8 billion years old, composed not only of matter and radiation, but dominated by something far stranger: dark energy, an unknown force driving accelerated expansion. Finally, the Planck satellite, launched in 2009 by the European Space Agency, carried the measurements to their finest resolution. Its detailed maps painted the most accurate picture yet of the infant cosmos, a portrait of energy and matter arranged in a delicate balance. Planck's data confirmed that ordinary matter, everything humans can see and touch, accounts for less than 5% of the universe. Dark matter makes up about 27%, and the rest, nearly 70%, is dark energy, the mysterious presence that governs the ultimate fate of space itself. But what these missions revealed was more unsettling still. The expansion of the universe was not slowing down, as gravity's pull might suggest. It was speeding up. Observations of distant supernovae in the late 1990s, led by 2 independent teams of astronomers, showed that galaxies billions of light years away were farther than they should have been if expansion were decelerating. The universe was accelerating, carried outward by a force no one could explain. The ancient hope of a cosmos that might eventually slow and settle was shattered. Instead, space itself seemed restless, driven by an unknown energy pressing outward with relentless insistence. Dark energy, as it came to be called, remains the most profound enigma in modern cosmology. It acts like a repulsive gravity, stretching space-time itself. Its nature is invisible, its origin uncertain. It might be a property of the vacuum, a cosmological constant as Einstein once imagined and then discarded, or it might be a field that evolves over time, changing the destiny of the universe as it fluctuates. Whatever it is, it has shifted the cosmic narrative. The universe is not slowing toward stillness. It is racing toward emptiness, a future in which galaxies rush so far apart that their light can no longer bridge the distance. Mapping the expansion has thus been more than an act of measurement. It has been an act of revelation. peeling back layers of cosmic history, exposing truths that overturn human expectation. The galaxies showed the pattern. The microwave background revealed the origin. Satellites traced the precise rhythm, and the accelerating discovery transformed the story into something stranger than imagination had prepared for. What began with Hubble's quiet measurements in the 1920s has become one of the greatest scientific endeavors in history. A project spanning continents, generations, and technologies, all in pursuit of a single question: how does space itself evolve? And in answering, science has found both clarity and mystery. Clarity in the shape of the cosmos, in the numbers that describe its age and contents. Mystery in the force that drives it apart, a presence more powerful than all the stars combined, yet unseen and unknown. The shift was profound. The universe, once thought eternal and steady, was revealed as dynamic and fragile. Then, the universe once thought destined to slow was revealed as racing away faster and faster. At every stage, the cosmic map has not provided closure, but deeper questions. And now, as instruments grow more powerful and surveys more complete, the human gaze presses further, seeking the answer that still eludes. Not only how the universe expands, but what awaits when this expansion reaches its end. At first, the story of cosmic expansion seemed almost intuitive. The Big Bang hurled galaxies outward, and gravity, the ancient binding force, would slow their flight. Over eons, the expansion would gradually decelerate, perhaps halting, perhaps reversing, perhaps drifting toward a delicate balance. It was a vision both dynamic and comprehensible, a universe propelled outward by its explosive birth, restrained by the invisible hands of gravity. But as the 20th century neared its end, new observations unsettled this simplicity. The universe was not slowing down, it was accelerating. This revelation was as unsettling as it was undeniable. Distant Type Ia supernovae, observed by two independent teams in the late 1990s, appeared dimmer than expected. Their faintness did not arise from error or dust, but from distance. They were farther away than they should have been if the universe's expansion was slowing. The conclusion was inescapable. Galaxies were racing apart ever faster. Something was pushing against gravity, overwhelming its eternal pull. The mysterious culprit was given a name: dark energy. Not a substance that could be seen, not a force that could be touched, but a mathematical presence, revealed only through its effect on the cosmos. It was as though space-time itself had acquired a restless urge to expand, as though emptiness carried within it a pressure that could not be contained. The contradiction was profound. Gravity, the force that binds galaxies, planets, and stars, is the architect of structure, the sculptor of order. Yet on the largest scales, it was being defeated. The same universe in which black holes collapse, matter into singularities, was now governed by a counterforce, invisible and relentless, stretching its fabric faster with each passing epoch. The cosmos seemed to contain two opposing wills, one pulling inward, one driving outward, locked in a struggle that determined the fate of everything. The philosophical implications were staggering. If expansion were accelerating, then perhaps it would never end. Galaxies would recede beyond visibility. The night sky, once filled with billions of suns, would grow sparse and silent. Civilizations born in the deep future might look to their heavens and see only their own stars, unaware of the grand cosmic story that unfolded before them. Expansion, if eternal, would not only carry galaxies apart, but also isolate every island of light into solitude. The universe would become a scattering of lonely embers in an ever-darkening sea. Yet even this vision contains uncertainty. Dark energy is not fully understood, and its future may not be fixed. Some theories suggest it is constant, a feature of space-time itself, akin to Einstein's abandoned cosmological constant. If so, acceleration will continue forever, an endless drift into emptiness. But other models hint at decay, that dark energy may change with time, weakening, vanishing, or even reversing. If it were to diminish, gravity might one day regain dominance, pulling galaxies back together in a final collapse. The Big Crunch. If it were to grow stronger, expansion could tear not only galaxies apart, but stars, planets, and atoms themselves, ending in the unimaginable violence of the Big Rip. Beneath these possibilities lies an even stranger truth. The balance of the universe is unimaginably fine. The density of matter and energy, the value of the cosmological constant, the equations of relativity, all are delicately tuned. A slightly stronger pull, and the cosmos would have collapsed long ago. A slightly weaker push and expansion would never have produced galaxies or stars. That the universe exists in such a precarious balance is one of the great mysteries of modern science. Is this delicate tuning coincidence, necessity, or evidence of deeper laws yet undiscovered? This fine balance leaves humanity standing on a precipice of knowledge. The universe is accelerating, yet its destiny is veiled. The constants that govern reality are measured with exquisite precision, but their origin remains hidden. In this contradiction lies a quiet terror. The universe is knowable, yet fundamentally unknowable. Its forces revealed, but their essence concealed. As astronomers chart galaxies, measure the faint echoes of the cosmic microwave background, and test the strength of dark energy, they press against the edges of this mystery. Each discovery refines the picture, but also deepens the question. Why does the universe expand faster? What is the true nature of the force that resists gravity? And above all, what fate awaits when its strength, whether constant or changing, finally reveals the ultimate shape of time? The deepening mystery of dark energy is not merely a problem of physics. It is a mirror to existence itself, a reminder that the cosmos is governed by laws both elegant and alien, delicate yet overwhelming. Gravity pulls, but the universe flees faster. Expansion accelerates, but its end remains hidden. Between these contradictions, humanity lingers, suspended in wonder and unease, carried forward on a tide whose source remains unseen. Every story whispers toward an ending, and the universe is no exception. From the faint afterglow of its fiery beginning, to the shimmering galaxies drifting outward, the cosmos carries within it the seeds of its own fate. Expansion may last forever, or it may turn upon itself. Its conclusion is written not in myth, but in physics, in the quiet interplay of matter, energy, and time. Yet the ending is not a single vision. It branches into possibilities, each supported by science, each haunting in its own way, each carrying the weight of finality. One vision is the Big Freeze. In this scenario, expansion continues endlessly, galaxies retreating farther until they slip beyond visibility, their light stretched into silence by the swelling fabric of space. Stars will live out their lifespans, consuming their fuel until none remain. The brilliance of galaxies will fade into cold embers, black dwarfs and neutron stars lingering in darkness. Over unthinkable timescales, even these remnants will decay. Entropy will claim all order, scattering energy into uniform stillness. The universe would not end in fire or collapse, but in quiet, a cosmos vast, empty, and cold, where time itself loses meaning. This is the ultimate stillness, the eternal night. But there is a more violent possibility, the Big Rip. If dark energy grows stronger with time, acceleration will not merely carry galaxies apart. It will tear apart the structures themselves. First, clusters of galaxies would dissolve. Then galaxies would unravel, stars set adrift. Later still, stars, planets, and moons would be torn from their orbits. As expansion grows unbearable, it would seep into the microscopic realm, pulling apart molecules, then atoms, then the very fabric of matter. Even space-time would rend itself apart. The universe would not drift into silence, but shatter into fragments, ending not with stillness, but with rupture. Another path looks backward, toward gravity's ancient pull. This is the Big Crunch. If dark energy weakens or reverses, gravity may halt expansion and turn it inward. Galaxies would fall toward one another. The sky would brighten not with creation, but with collapse. Stars would collide, temperatures would soar, and the cosmos would grow denser with every passing moment. Eventually, space itself would implode, all matter compressed into a single point of unimaginable density, echoing the moment of origin, but in reverse. The universe would end, not with silence or tearing, but with its own inward fall, consumed by the gravity that first allowed it to exist. Yet even within this catastrophic vision lies another possibility, the Big Bounce. Perhaps collapse is not the final word. Perhaps compression gives rise to another birth, as energy and density ignite a new expansion. In this view, the universe is not a singular story, but a cycle. Expansion, collapse, rebirth, repeated across endless ages. Each cycle would erase the scars of the last, yet perhaps leave hidden imprints, faint patterns in the cosmic background. If true, then what is called the beginning may only be one of countless beginnings, and what is called the end may only be another doorway. Each of these theories is more than physics. They are visions of destiny. The Big Freeze carries the poetry of silence, a universe fading like a candle. The Big Rip holds the terror of violence, a cosmos torn apart by its own emptiness. The Big Crunch offers the symmetry of return, a fall back into the gravity from which it sprang. The Big Bounce extends hope of renewal, suggesting no end at all, but eternal cycles of death and rebirth. Humanity stands far from certainty. The measurements of dark energy, of cosmic density, of the universe's expansion remain incomplete. Satellites like WMAP and Planck, telescopes peering deeper into the redshift of distant galaxies, refine the picture, but the future remains veiled. What is known is only that the universe is expanding and that expansion accelerates. The fate of all things, of galaxies, of stars, of atoms, depends on the hidden nature of the force driving it. The universe may freeze, it may rip, it may collapse, it may bounce. Each outcome speaks not only of physics, but of philosophy, of how endings define stories. And while humanity may never witness which future comes to pass, the knowledge that the cosmos itself has an ending, that even eternity carries a fate, shapes how existence is understood. For now, the universe continues its silent drift, its fate uncertain, its endings plural. In the vastness, the question remains suspended. Will it end in fire, in silence, in collapse, or in renewal? The answer lies in forces unseen, written in constants yet to be understood. Until then, the universe moves onward, carrying its mystery, carrying its inevitability. In the silence of the universe, numbers whisper. Beyond the sweep of galaxies, beyond the glow of stars, lies a language so abstract, yet so precise, that it traces the entire destiny of existence. This language is mathematics, and through it, physicists glimpse not only how the cosmos expands, but how it may one day end. Equations do not merely describe the universe. They are its heartbeat, its rhythm, its hidden script. At the foundation of this script lies Albert Einstein's general theory of relativity. Published in 1915, it revealed that space and time are not rigid backdrops, but a dynamic fabric, bending under the weight of matter and energy. In its curvature lies the story of motion, gravity, and light itself. Within Einstein's field equations, a set of symbols no larger than a page, resides a truth vast enough to govern galaxies. These equations bind geometry to destiny, suggesting that the structure of space-time dictates how the universe evolves across billions of years. When these equations are applied not to stars or planets, but to the universe as a whole, they give rise to a framework that allows the cosmos to be treated as a single object, a dynamic, evolving entity. From this pursuit came the Friedmann equations, born in the 1920s through the insight of Russian physicist Alexander Friedmann. Building upon Einstein's relativity, he introduced a way of measuring how the scale of the universe changes with time. These equations are, in essence, the clockwork of cosmic expansion. They describe whether the universe slows, halts, collapses, or accelerates, a spectrum of possible fates hidden in mathematics. At their core, the Friedmann equations rely on a handful of fundamental variables. The energy density of the universe, the sum of matter, radiation, dark matter, and dark energy, acts as a kind of weight against the fabric of space-time. Too much density and gravity dominates, pulling the universe inward toward collapse. Too little and expansion rushes, outward unchecked, carrying galaxies beyond sight. Balanced perfectly, expansion slows asymptotically, never collapsing, never tearing apart, but lingering on the edge of stillness. The constants within these equations carry extraordinary power. The gravitational constant, the Hubble parameter, the cosmological constant. Each is a delicate dial, fine-tuned across magnitudes. Even the slightest change could have yielded an entirely different universe, a fraction more matter density. An expansion might never have begun, with the universe collapsing back into itself before galaxies or stars were born. A fraction less, and expansion would have accelerated so rapidly that structure never coalesced, leaving a barren cosmos of diffuse particles. The balance is so precarious that physicists often speak of cosmic fine-tuning, as though existence itself were perched upon a knife's edge of possibility. Dark energy, represented in many equations as the cosmological constant, L, introduces its own enigma. Einstein once introduced it reluctantly, to maintain a static universe, before calling it his greatest blunder. Yet decades later, it emerged again, reinterpreted as a force of acceleration. Within the Friedmann equations, L is not merely a mathematical placeholder, it is a measure of how the vacuum of space influences expansion. If it remains constant, the universe accelerates toward the big freeze. If it grows stronger, it could propel a big rip. If it weakens or reverses, it could allow for a future collapse, a big crunch. Thus, the fate of everything may hinge upon the precise value of a constant embedded in Einstein's field equations. These equations, written in the abstract symbols of mathematics, describe arcs of billions of years. They are timekeepers, not of human lives, but of cosmic epochs. Their trajectories extend beyond the imagination, predicting the dimming of galaxies, the collapse of stars, the expansion of space-time itself. They reveal that the fate of the cosmos is not a matter of mythology, but of numbers, equations, etched into the very laws of physics. And yet, for all their precision, uncertainties remain. Observations of the Hubble constant, the present-day rate of expansion, yield conflicting results. Measurements from the cosmic microwave background, captured by satellites like Planck, differ from those derived from the distance of nearby galaxies. This tension, known as the Hubble tension, ripples through cosmology, suggesting that hidden physics may still lurk within the equations. Perhaps dark energy is not constant. Perhaps new forces exist, unimagined in Einstein's time. Perhaps the mathematics of fate is not yet fully written. What these equations reveal most profoundly is fragility, a universe balanced delicately between expansion and collapse, between silence and fire. Tiny shifts in the initial conditions, imperceptible in their scale, decide whether space races outward forever or recoils inward to a point. In this sense, the cosmos is both infinite and precarious, a structure whose destiny is dictated by constants no wider than a line of numbers. The Friedmann equations stand not merely as calculations, but as visions. They project forward into futures where stars fade, where space tears apart, where universes collapse and rebound. They remind humanity that time is not endless, that eternity itself may bend under the rules of physics. In the quiet language of mathematics, they write the possible ends of everything. For in the end, fate is not carved in stone, but in equations, a delicate balance of density, energy, and geometry. And as long as those equations remain only partially understood, the final destiny of the universe remains suspended, not in certainty, but in mystery. The universe is vast, but the pursuit of its truth begins with fragile instruments forged by human hands. In the immensity of cosmic time, humanity is still young, a species only recently able to lift its gaze beyond the faint veil of its atmosphere. Yet with mirrors polished to perfection, detectors cooled to near absolute zero, and algorithms capable of stitching together faint whispers of light, astronomers now wield tools powerful enough to touch the fabric of destiny itself. Each instrument, each observatory, is a question cast into the void. What drives expansion? Will it last forever? Will it end? High above Earth, the James Webb Space Telescope unfolds like a golden flower in the vacuum of space. Its mirror, more than 6 meters wide, is the largest ever sent beyond the atmosphere. Shielded by 5 layers of silvered fabric, it stares not only into the deep past, but into the faint present, measuring the dim light of galaxies whose signals carry the signature of expansion. By capturing red-shifted light with exquisite precision, Webb extends Hubble's legacy, probing how galaxies formed and how the accelerating cosmos sculpted their distribution. Its sensitivity makes it a sentinel of dark energy, capable of tracking the fingerprints of the universe's invisible driver across billions of years. On Earth, in the deserts of Chile, the Vera Rubin Observatory is preparing to map the sky with a rhythm never before achieved. With its 8.4-meter mirror and the largest digital camera ever constructed for astronomy, it will scan the entire visible sky every few nights, building a dynamic atlas of the cosmos. Its true power lies not in single images, but in the accumulation of change. By watching how billions of galaxies drift ever farther apart, it will test the universe's expansion with unprecedented detail. Within its data may lie answers to the most haunting question: is dark energy constant, or does it evolve with time? Beyond both of these, in the quiet of interplanetary space, the Euclid mission, launched by the European Space Agency, carries a similar purpose. Its instruments are designed to map the geometry of the cosmos, tracing how structures of galaxies bend under gravity, how space curves, how expansion shifts the tapestry of the universe. By combining weak gravitational lensing with galaxy clustering, Euclid seeks to measure the equation of state of dark energy, the precise relationship between its pressure and density. If this equation deviates even slightly from the cosmological constant, it may reveal that dark energy is not a simple constant at all, but a dynamic field, one that could change, decay, or even vanish. Yet the investigation does not stop with telescopes. At the smallest scales, in underground caverns and vast particle accelerators, physicists seek the roots of expansion in the quantum vacuum itself. The Large Hadron Collider at CERN smashes protons together at near-light speed, probing energies where virtual particles flicker into being and vanish. Within this seething foam lies the possibility that the vacuum of space is not stable, that it holds hidden energies capable of shaping the fate of the cosmos. If quantum fluctuations govern dark energy, then its nature may be revealed not in galaxies drifting apart, but in the mathematics of fields invisible to the eye. Together, these instruments form a symphony of inquiry. Telescopes stretch across the cosmos, particle detectors plunge into the subatomic, satellites orbit beyond Earth's interference. All are aimed at a single enigma. Why does expansion accelerate, and will it end? The hope is that one discovery, a signal from the distant past, a shift in a constant, a particle born in a collider, may offer clarity, but even as precision grows, mystery deepens. The more data is gathered, the more subtle the cosmos appears. Webb's deep fields reveal galaxies too mature for their age, hinting at physics beyond current understanding. Measurements of the Hubble constant remain in tension, with one set of instruments suggesting one rate of expansion and others a different one. This unresolved conflict whispers of unknown forces at work, of equations incomplete, of laws not yet written. The search is not merely technical, it is existential. Each mirror polished, each detector cooled, each launch undertaken carries within it humanity's attempt to see the end of time. For what these instruments measure is not only expansion, they measure fate itself. They chart the balance between silence and collapse, between endless cold and violent rupture. In their data lies the possibility of an answer to the oldest of questions. Will the cosmos endure without end? Will it collapse into itself? Or will it unravel, atom by atom, in a cosmic shattering? For now, the universe remains unresolved, and the tools of inquiry continue their vigil. Webb gazes backward. Rubin prepares to watch the present unfold. Euclid maps geometry across the dark fabric, and colliders reach inward to the heart of matter itself. Each is a lantern in the abyss, illuminating fragments of truth. But the full shape of destiny remains hidden, suspended in the silence between data points, awaiting discovery. And so, humanity continues to build, to search, to question, knowing that to seek the fate of the universe is also to seek the fate of everything within it. Every story has a horizon, and in cosmology, that horizon is the fate of expansion. The universe drifts outward in silence, galaxies carried away on currents of dark energy, stars glowing and fading in an ocean without shore. Yet one question lingers like a shadow at the edge of knowledge. What happens if expansion halts? Would the universe simply slow, resting at some eternal stillness? Or would halting expansion mean something deeper, something stranger, the unraveling of time itself? Expansion is not merely a stretching of distances. It is the very rhythm by which existence unfolds. Space grows, and in its growth, time finds its direction. This is the arrow of time, the steady march from past to future, woven into entropy, into the second law of thermodynamics, into the deep fabric of the cosmos. As galaxies drift apart, as energy dissipates, time moves forward, never backward. If expansion were to halt, the arrow of time might lose its compass. A universe without expansion may be a universe where the meaning of before and after begins to blur. Physicists have long debated the relationship between space, expansion, and time's one-way flow. Entropy rises as the universe expands, disorder growing with each passing epoch. If expansion stops, does entropy reach a limit? Could time itself as a concept dissolve into stasis? The question is more than philosophical. It is encoded in the mathematics of cosmology, where the evolution of the universe dictates the unfolding of causality itself. Quantum theory adds another layer of uncertainty. Within the vacuum of space, particles flicker into being and vanish again, an invisible foam of fluctuations. Some physicists speculate that what is called empty space may be metastable, a false vacuum. If this is true, then the universe lives precariously, perched on a plateau of temporary stability. A sudden shift, a quantum transition, could collapse this vacuum into a more stable state, releasing catastrophic energy, rewriting the laws of physics, and reshaping space-time itself. In such a scenario, expansion halting may not be a gentle slowing, but a sudden transformation, an unmaking of the universe as it is known. This leads to an unsettling thought. If expansion is tied to the very essence of time and reality, then its end may not simply mean stillness. It may mean erasure. The collapse of the false vacuum, or the freezing of the cosmic arrow, could dissolve the concepts of existence, of history, even of physics itself. In such a fate, nothing would remain. No stars, no galaxies, no observers. Only a silence, beyond comprehension, where even the measure of time ceases. And yet, not all speculation is so final. Some theories suggest that halting expansion may lead not to death, but to transformation. If space ceased to stretch, the balance of forces might shift, giving rise to new physics. Perhaps the cosmos could fold into dimensions unseen or transition, into a phase of reality where time behaves differently. no longer a linear march but something cyclical, elastic, or entirely alien. The end of expansion may not mean the end of existence, but its metamorphosis into something beyond recognition. This is the paradox at the heart of cosmology. The universe is measured, mapped, and described with exquisite precision, yet its ultimate fate remains unknowable. The instruments of science peer backward nearly to the dawn. They measure the faint whispers of cosmic radiation. They map galaxies across billions of light years. But the question of what lies beyond the edge of expansion remains unanswered. Is it silence, rupture, rebirth, or transformation? For humanity, contemplating such possibilities is both terrifying and profound. To consider that time itself may halt is to confront the fragility of everything. To imagine transformation instead of erasure is to accept that existence may continue, but in forms unimaginable. The cosmos does not promise permanence. It offers only change, only becoming, only mystery. And so the question endures. If expansion halts, does the universe end with it? Or does it awaken into something new, carrying forward a story beyond comprehension? Perhaps the final truth is that endings are illusions, that even the cessation of expansion may be but another chapter in a book whose scope no mind can contain. The universe speaks in lifetimes far longer than stars, far greater than galaxies. Against that scale, humanity is a fleeting spark, a brief consciousness ignited in the vast darkness. And yet, within this spark lies reflection, the ability to ask not only how the cosmos expands, but what that expansion means, to wonder at its inevitability, its indifference, and its quiet path towards silence. The great irony is this: intelligence arose in a universe already marked by decay. The cosmos has been expanding since its birth nearly 14 billion years ago. Stars have lived and died countless times. Galaxies have merged and scattered. And only now, in this thin slice of cosmic history, does one small species contemplate what it means to exist in a universe that is itself destined to fade. It is as though awareness awoke just in time to witness the evidence of its own impermanence. If expansion continues as the data suggests, the universe of the far future will be unrecognizable. Civilizations that arise billions of years from now may live beneath skies emptied of wonder. Galaxies beyond their own will slip forever out of sight, their light stretched into invisibility by the relentless expansion of space. The cosmic microwave background, the faint afterglow of the Big Bang that today bathes the universe, will grow so diffuse, so cold, that no trace of it will remain detectable. Future astronomers, if such beings exist, may find themselves in isolation, unable to see the evidence of origins, unable to know that other galaxies once filled the sky. For them, the universe will appear small, static, and lonely. This loneliness extends not only across time, but across space. As galaxies recede, as distances grow, the possibility of communication across the cosmic void diminishes. Civilizations, separated by tens of millions of light years, may attempt to speak, but expansion stretches their messages into silence. The very fabric of reality conspires against connection, ensuring that intelligence, no matter how advanced, will one day be bound by isolation. The universe is not cruel in this. It is indifferent. Its laws unfold without malice, without intent. Expansion does not conspire to erase memory. It is simply the outcome of equations written into space-time itself. Yet indifference can feel like cruelty to beings who long for meaning. Humanity finds itself caught in this paradox, aware of a universe vast beyond comprehension, yet destined never to reach most of it. Conscious of time on scales far greater than its own existence, yet unable to escape its brevity, and, still, in this awareness lies a strange beauty. To know the universe will fade is also to know that existence is rare, fragile, and precious. The fact that a fleeting species, on a small world, orbiting an ordinary star, can measure the motion of galaxies, trace the afterglow of creation, and imagine the universe's end. This is a triumph not of permanence, but of presence. For however brief, humanity has looked into the abyss and found not only darkness, but understanding. The dying cosmos is not a story of despair, but of perspective. Expansion ensures that nothing lasts forever. Stars fade, galaxies drift away, time carries all things forward. Yet in that transience lies meaning. The fleeting spark of life shines more brightly because it is temporary. The night sky glows with a beauty heightened by the knowledge that one day it will be gone. Perhaps this is the role of consciousness in the universe, not to halt expansion, not to escape its destiny, but to bear witness, to marvel at the improbable fact of existing between beginning and end, to create memory, art, science, and meaning in a cosmos that offers none of its own, to live knowing that the universe will forget, and yet to live anyway. The human place in a dying cosmos is not one of mastery, but of reflection. Expansion reminds humanity that it is small, fragile, impermanent. Yet it also reminds that it is capable of wonder. And in the end, wonder may be the most enduring legacy of all. From the first moment of thought, space has been imagined as a stage, a vast emptiness upon which matter performs its fleeting play. Yet modern science reveals it to be more than a backdrop. Space is not absence, but substance. It bends, it stretches, it carries galaxies upon invisible currents of expansion. It is the silent architect of time's arrow, the unseen loom upon which the fabric of existence is woven. To speak of the end of expansion, then, is not to speak merely of distance or of emptiness, but of the fate of this very fabric itself. The expansion of the universe is not eternal in the sense of certainty. It is eternal only in the sense of possibility. Some models suggest it will accelerate forever, scattering galaxies into eternal exile. Others predict a reversal, a collapse into fire and density. Still others imagine a quiet fade, a transition into stillness. But beneath all these scenarios lingers the deeper question: what becomes of space itself once the music of expansion ceases? If space is truly alive, a dynamic field, restless and shifting, then its ending may be no ending at all. The cosmos could shed its current form the way a star sheds its outer layers, revealing a transformation beneath. In the language of physics, this might appear as a quantum phase transition, a shift of the vacuum itself into something utterly alien. In the language of philosophy, it is the death of one reality, giving birth to another. The cosmos may not vanish, but metamorphose into a geometry beyond comprehension, into dimensions hidden from sight, into laws no current mathematics can yet write. There is a haunting symmetry in this idea. Just as life on Earth arises and decays, just as stars are born from the ashes of others, the universe itself may cycle through forms, each expansion and collapse no more final than the breath of a living being. Endings, perhaps, are illusions, a word shaped by the limits of perception, not by the truth of eternity. The greatest mystery is not whether expansion will end, but whether such an end is even meaningful. Time itself is tied to the rhythm of space. If space ceases to stretch, does time itself dissolve? Or does it continue in another register, invisible to the remnants of a dying cosmos? In the silence after expansion, would there still be a measure of before and after? Or only an eternal present? The human mind cannot reach that horizon. Equations gesture toward it. Telescopes stretch their vision across billions of light years, but the ultimate nature of space remains hidden. What is certain is only this: the universe is not a closed story, not a solved riddle. It is a question without an answer, echoing endlessly across its own immensity. In that echo lies the final poetry. When expansion ends, space may not vanish into nothingness. It may become something stranger than imagination can contain, something more profound than language can hold. And so the story closes, not with resolution, but with mystery. The kind of mystery that humbles, that unsettles, that ignites wonder. The cosmos endures not as an answer, but as a question. And in the end, It is the question itself that outlives all things.